Um, I want you to imagine just for a second that you're standing in the middle of this dusty, sprawling, completely empty dirt field.
Right, just a massive blank slate.
Exactly. The sun is beating down on you, and in your hands, you're holding the final approved blueprints to a billion-dollar mega project.
That is a heavy stack of paper.
It really is. And you look out over the horizon, and maybe you're picturing a massive, miles-long, new oil refinery.
Yeah.
You know, a maze of steel pipes stretching as far as the eye can see.
Or it could be a data center.
Yeah, a hyper-secure, state-of-the-art data center. The kind that pulls enough electricity to power a small city just to run the next generation of AI.
Or even a cutting-edge EV battery plant.
Right. Something poised to revolutionize clean energy. So you look to your left, and the crews are in their hard hats, ready to go. You look to your right, and there are these massive yellow backhoes and excavators lined up, engines idling.
Everyone is just waiting for the green light.
You are itching to give the signal to break ground. But here is the massive, really counterintuitive secret that separates the true masters of industry from the spectacular career-ending failures.
And it's a harsh reality to face.
It is. Because before a single shovel even hits that dirt, the most crucial, monumental decisions for that entire project have already been made.
That's exactly right. It's a reality that can be really difficult to wrap your head around when you are staring at an empty field, but it all comes down to a fundamental law of capital projects.
Right.
In the industry, it's known as the cost influence curve. It is, on the surface, a very simple graph. But the mathematics of that curve dictate the fate of billions of dollars.
Which is terrifying if you get it wrong.
Completely terrifying. If you look at the life cycle of any massive physical project, more than half of your opportunity to influence the final total cost of that facility happens incredibly early on.
Like before the tractors even show up.
Long before. We are talking about the period of time before the heavy, detailed engineering even starts.
Because, and I think this is something we can all relate to, even if you're just renovating a kitchen, it is always cheaper to erase a pencil line on a piece of paper than it is to tear down a poured concrete wall.
Oh, absolutely. The cost difference is exponential.
That early conceptual phase is the absolute cheapest time to fix a billion-dollar mistake. So, I want to formally welcome you to this deep dive.
We have a lot of ground to cover today.
We really do. If you're joining us today, you are probably the kind of person who looks at a massive suspension bridge, or a skyline-dominating skyscraper, or a sprawling industrial complex, and wonders how on earth do the biggest, most complex things in the world actually get built without just collapsing into financial ruin.
It is a minor miracle of human coordination every time it happens.
It really is. How do humans coordinate something that massive? Well, that is our mission today. We have gathered a massive stack of sources for you. We're talking dense project management frameworks, highly technical engineering white papers, industry articles, consulting guidelines.
It's a lot of reading.
A ton of reading. And we are going to distill them to understand the ultimate cheat code for massive capital projects. It's a framework called front-end loading, or FEL for short.
It's an incredibly powerful framework. Depending on the specific industry you are in, you might also hear it referred to as front-end planning, or FEED, or pre-project planning.
Right, the terminology shifts around.
It does, but regardless of the specific name, FEL is a highly structured, fiercely disciplined, stage-gated approach to shaping a project early in its life cycle.
It's essentially the philosophy of doing the right project the right way long before you ever try to do it fast.
Yes, and I want to set the tone for you right out of the gate here, that this isn't just a conversation about building chemical factories or laying natural gas pipelines.
No, it's much bigger than that.
At its absolute core, front-end loading is a masterclass in risk management, resource allocation, and critical decision-making under pressure.
Because you're dealing with so many unknowns.
Exactly. It's a framework that requires a team to confront ambiguity head-on. The critical thinking skills it demands are universally applicable to almost any complex endeavor you might be facing in your own life or your career or your business.
Okay, let's unpack this acronym for a second, just to make sure we are crystal clear before we get into the weeds. FEL, front-end loading.
Let's do it.
From what I'm reading in these sources, the front stands for being hyper-focused on the earliest stages of the project lifecycle.
Right, the very beginning.
And then the end targets the front end of your executive decision-making, right before you make those terrifying major financial commitments.
Before you open the corporate checkbook.
Exactly. And the loading is the physical action. You are concentrating all of your intellectual effort, your analysis, and your scope definition up front. You are quite literally front-loading the hardest intellectual work.
You are concentrating the mental heavy lifting at the beginning. The entire goal is to systematically de-risk the delivery of the project before major funds are committed.
And it's important to note, this isn't some trendy new management fad, right?
Not at all. It didn't come out of a Silicon Valley incubator last year. The roots of FEL trace all the way back to the 1980s,
In the heavy industries.
deeply tied to what we call the process industries. We are talking massive oil and gas exploration, complex petrochemical refining, extractive metallurgy, mining.
The stuff that requires unbelievable amounts of capital.
Exactly. And from those heavy industrial origins over the last 40 years, it has naturally expanded out into heavy civil infrastructure, waste-to-energy plants, and massive pharmaceutical manufacturing.
In reading through these white papers, it seems like the reason this framework emerged in those specific heavy-duty sectors is directly tied to a massive amount of corporate pain.
That is the perfect way to describe it. A lot of financial pain.
These facility owners and the massive EPC firms, which stands for engineering, procurement, and construction contractors, they were bleeding money in the 80s and 90s.
They were observing a brutal, undeniable trend. Almost all of their catastrophic cost overruns and massive schedule delays could be traced back to one single root cause.
Weak early definition.
That is the exact phrase, weak early definition. These companies were rushing.
The executives wanted to see physical progress.
Right, they pushed their teams, so they had an unclear scope of what they were actually trying to build. They were making rushed, emotional decisions on their core engineering concepts and moving forward with completely undercooked execution strategies.
And in these specific industries, the penalty for that kind of rushing is just fatal.
You are dealing with highly capital-intensive, incredibly long life cycle projects. You are spending hundreds of millions, often billions of dollars over a span of 3, 4, or 5 years before the facility produces a single drop of refined product.
Or generates a single dime of revenue for the company.
Precisely. When your capital exposure is that high and your timeline to profitability is that long, ambiguity is your absolute biggest enemy.
You cannot afford to just figure things out as you go.
You just can't. FEL was born out of sheer necessity to force a disciplined, heavily gated path to systematically reduce that uncertainty before the massive execution machinery starts grinding.
You know, it's such a fascinating contrast to the dominant business philosophies we see a lot today, particularly in the tech sector, which really dominates our culture's idea of project management right now.
The agile mindset.
Exactly. Modern agile workflows are everywhere. The mantra is always build a minimum viable product, get it out there, fail fast, iterate on the fly, pivot.
Which works beautifully when your product is software code.
Right. You can push an update to an app overnight while your users are sleeping. But in heavy construction and massive capital projects, you can't exactly iterate on a custom-built 500-ton chemical reactor that takes 18 months just to forge in a specialized steel mill.
No, there is no Control-Z or undo button on a construction site.
You can't just hit refresh on a steel beam.
Exactly. You cannot release a beta version of a poured concrete foundation and see how the users like it.
That would be a disaster.
It would. If you realize halfway through construction that you need to move a primary load-bearing column by just 3 feet because someone miscalculated the size of a boiler, the cost multiplier to demolish and rebuild that is astronomical.
So front-end loading is basically the rigorous physical antidote to the build and iterate mindset.
It's the philosophy you must adopt when the physical stakes of your project are permanent.
That makes perfect sense.
Yeah.
You cannot agile your way out of a bad foundation. So if the cost penalty for changing your mind during construction is that massive, how do these project managers actually prevent it?
That brings us to the actual mechanics of the process.
Right. What does the physical process of getting from a vague napkin sketch to a bulletproof blueprint actually look like? The sources outline that this entire front-loading philosophy is broken down into highly specific sequential stages.
Usually divided into FEL1, FEL2, and FEL3.
And sometimes you'll see reference to a pre-stage called FEL0 and a post-stage called FEL4. Let's walk through what actually happens at each of these steps because it really is a masterclass in organized thinking. Let's start with FEL0.
FEL0 is often called the conceptualization phase. Think of this as your absolute earliest feasibility check.
Like when someone just has a wild idea.
Yes, an executive has an idea in the shower or a market analyst spots a trend. At this point, the costs to the company are incredibly low.
The sources say it's usually just 1 to 5% of the total project investment.
Exactly. You are really just asking the most basic, fundamental questions. Is this even physically possible? And is there an economic business case that justifies even looking into this?
It's just testing the waters, a sanity check.
That's all it is.
But let's say the executive's idea passes that sanity check. That moves the team into FEL1. The sources call this phase opportunity framing, or the option study.
And this requires a bit more investment.
All right, this phase costs roughly 5 to 15% of your total early investment. And the key question you're trying to answer in FEL1 is, what are my options to achieve my project goals?
The critical thing here is that you aren't locking anything in yet. You are mapping the option space.
You're casting a really wide net.
Yes. In FEL1, you are developing what the industry calls rough order of magnitude estimates.
ROM costs.
Right, ROM costs. Think of a ROM estimate as that napkin sketch we talked about. You are looking at high-level feasibility.
Like doing preliminary site mapping. Like, should we build this in Texas or should we build this in Ohio?
You are screening out the obviously bad ideas. You are asking high-level technical feasibility questions. Can this proposed technology even be integrated into our existing corporate systems?
Do we have the internal technical expertise to pull this off, or do we need to hire an outside firm?
Are there better, more efficient technologies on the market that we haven't considered? You are also doing your first real risk assessment and looking at the major macro-level environmental compliance implications.
I want to bring up a specific example from one of the engineering white papers we read, because it blew my mind and really illustrated this point for me.
Let's hear it.
Now, I am definitely not a mining engineer, so bear with me, but it was a case study about a mining company that needed to process something called nickel laterite ore.
Ah, yes. A notoriously complex metallurgical challenge.
Right. So at the FEL1 stage, the project team realizes that to get the valuable nickel out of this specific type of rock, they basically have two massive diverging paths they could take.
Two completely different processing methods.
Exactly. They could build either a pyrometallurgical processing plant, and let me make sure I'm getting this right, which uses extreme blast furnace heat to melt the metal out.
That's correct.
Or they could build a hydrometallurgical processing plant, which uses complex aqueous chemistry and massive acid baths to dissolve the metal out.
Those are two completely different universes of engineering.
Right. One is all about handling molten rock, and the other is all about handling highly corrosive liquids.
And that is the beauty of FEL1. If you didn't have this framework, an eager executive might just say, I know a guy who builds blast furnaces. Let's just go with heat.
Just skip the research and start building.
Exactly. But in FEL1, you are forced to study both options thoroughly. You dedicate engineering hours to looking at the pyrometallurgical option, and you dedicate hours to looking at the hydrometallurgical option.
You compare their rough costs, their environmental footprints, and their efficiency for your specific geography.
You pick the absolute best one, and then you move forward. You do not try to fully design both, because that would waste millions of dollars, but you rigorously explore the options before committing.
And that leads perfectly into the next phase, because let's say for our hypothetical nickel plant, the data comes back and we officially pick the heat-based pyrometallurgical plant in FEL1.
You've made your choice.
Right. Now we transition into FEL2.
What's fascinating here is the psychological shift that has to happen within the project team as you move from FEL1 to FEL2. Well, in FEL1, your mindset is expansive. You are exploring broadly. You want wild ideas. You want options. You want brainstorming.
Anything goes, essentially.
But as you transition into FEL2, you have to brutally shift gears and start converging thoughtfully.
Narrowing it down.
Yes. FEL2 is known as concept selection or preliminary design. This requires spending a bit more money, usually about 10 to 20% of your total front-end budget.
And the driving question fundamentally changes.
Yeah, it changes from what are my options to which specific configuration of this option is the best.
So, keeping with our example, we already decided we are using heat. We aren't questioning that anymore. In FEL2, we are comparing viable concepts for that specific type of heat-based plant.
Exactly. Do we use rotary kilns or electric arc furnaces? How big should they be?
You are no longer questioning the core technology. You are selecting the preferred alternative within that technology.
In FEL2, the engineers are drafting preliminary physical layouts. They're defining the performance criteria, like how many tons of ore does this plant need to process per day to be profitable?
And they are creating a highly critical document called a basis of design draft.
You are asking incredibly pointed questions now. What specific grades of steel do we need for these furnaces?
What is the optimal system configuration to balance the initial construction cost with long-term performance and energy efficiency?
You are starting to engage vendors to screen their specific proprietary technologies.
And from what I read, this is also where your cost estimates start to get much more serious. We aren't doing the napkin math ROM estimates anymore.
No, the napkin is gone. In FEL2, your cost estimate accuracy gets much tighter.
The industry categorizes these estimates by classes, right?
Yes. In FEL1, you might be at a Class 5 estimate, which means your total cost could realistically be off by 50 to 100%. It's a ballpark guess.
But by the time you finish FEL2,
You are moving into what the industry calls a Class 4 or Class 3 estimate range. You have done enough preliminary engineering that your margin of error is narrowing down.
you're also building a comprehensive integrated risk register.
And not just listing things that could go wrong, but developing actual funded plans on how to mitigate those risks.
Okay, so the team does all that work, and management agrees that this specific furnace configuration is exactly what they want to build. Now we cross into the heaviest phase of the early work, FEL3.
This is a massive lift.
It is. This is known as project definition, or often referred to as FEED, front-end engineering design.
This phase alone eats up 15 to 30% of the total project investment.
The question here is no longer what are we doing or which configuration is best. The question is strictly how exactly, down to the bolt, do we build this?
To use a relatable analogy, if building a mega project is like planning a massive complex wedding.
Oh, I like this.
FEL1 is deciding the grand vision. Are we eloping? Are we doing a small church wedding? Or are we doing a 500-person destination beach wedding?
Let's say you choose the beach.
Right. So FEL2 is evaluating the specific beaches. Are we going to Hawaii, Mexico, or Florida? You weigh the costs, the weather risks, and you pick Mexico. FEL3 is where you lock it all down. You are assigning the exact seats, you are locking in the specific catering menu, you are choosing the exact flowers, and you are signing the massive non-refundable deposits.
I love that analogy.
Yeah.
Because if you try to change the catering menu or the seating chart after FEL3, say, on the morning of the wedding, which would be the execution phase, it is going to be absolute expensive chaos.
Exactly. FEL3 is about removing ambiguity entirely from the construction process.
You are fully defining the scope to what is called an investment grade standard.
This is where the engineers really go to work and produce massive amounts of documentation. They produce P&IDs.
Which stands for piping and instrument diagrams.
Yes. These are the intricate schematics that show exactly how every single pipe, valve, and sensor connects in the entire plant.
They finalize the definitive basis of design.
And they build out the work breakdown structure, or WBS.
Let's pause there for a second. What exactly is a work breakdown structure?
A work breakdown structure is essentially taking a massive, overwhelming project, like build a billion-dollar refinery, and hierarchically breaking it down into smaller, manageable, and highly specific tasks.
So making it bite-sized.
Exactly. It breaks the project into phases, deliverables, and work packages until you get down to tasks that can actually be assigned to a specific crew, tracked, and costed.
So instead of just build refinery on a whiteboard,
It's pour foundation for Unit A, erect steel for Unit A, install pump 1 in Unit A. It's the ultimate to-do list.
got it. That makes perfect sense. So in FEL3, you are building that massive to-do list, you are writing the contracting and procurement plans, and you are building a highly detailed schedule.
A schedule that identifies the critical path.
The sequence of tasks that determines the absolute minimum time needed to complete the project.
Right. And your cost estimate here gets incredibly sharp.
You're moving to a Class 3 or even a Class 2 estimate.
You have actual quotes from vendors. You know exactly how many cubic yards of concrete you need.
So the FEL3 package is basically the definitive heavy binder of documents that a project manager slides across the mahogany table to the CEO.
And says, this is exactly what we are going to do, this is exactly how long it will take, and this is exactly what it will cost. Sign here.
And once that is signed, that leads us finally to FEL4, which is project execution and detailed engineering.
This is what most people picture when they think of construction.
It's the procurement of the heavy materials, the pouring of the concrete, the welding of the steel, and eventually the startup of the facility.
And this represents the vast bulk of the money.
Anywhere from 50 to 70% or even more of the total project investment is spent right here.
But the crucial takeaway, the entire point of this philosophy, is that FEL4 only goes smoothly and only stays on budget because of the rigorous, disciplined, forced convergence that happened in FEL 1, 2, and 3.
You explored wide, you locked the concept, you defined the execution down to the bolt, and then you spent the big money.
That is the sequence that saves billions.
Okay, but as I'm looking at this whole structure, I'm trying to put myself in the shoes of a project manager.
Right, the person actually on the ground.
If my boss, the CEO, is breathing down my neck, demanding to see backhoes in the dirt before the next quarterly earnings call, what is stopping me from just rushing the process?
That is the eternal struggle in project management.
Right. What stops a team from just breezing through FEL1, printing off some vague, half-baked documents, and rushing right into FEL3 just to look busy and appease the boss?
Human nature wants to rush.
Exactly. How does the industry actually enforce this discipline? And that brings us to the mechanism of control, the toll booths.
You've hit on the exact human vulnerability here, the urge to just get moving. To counter this, FEL relies entirely on stage gates.
You cannot just seamlessly slide from FEL1 to FEL2 because you feel like it.
No, between every single FEL stage, there is a formal hard stop, a governance gate.
So you have Gate 1, which is the opportunity gate between FEL1 and 2.
You have Gate 2, the select gate between FEL2 and 3.
And then you have the big one, Gate 3, which is the define or approve for construction gate.
I see this referred to in the sources as the FID, the final investment decision.
Yes, the final investment decision. And I cannot overstate the gravity of Gate 3.
It's the point of no return.
This is the critical juncture where the main project funding is officially approved by the corporate board or the executive steering committee.
This is when the actual purchasing of heavy hardware begins.
The multi-million-dollar turbines, the thousands of tons of structural steel, the custom chemical reactors, up to 80% of the project's total finances are legally allocated and committed at this single gate.
Here's where it gets really interesting. 80% of the money drops at Gate 3. I mean, think about the pressure in that boardroom.
It's immense.
That means the accuracy of that FEL3 engineering package literally makes or breaks the financial future of the entire endeavor, and potentially the company.
It's true. If your FEL3 estimate is off by 20% on a $2 billion project,
You are in a $400 million hole before you even pour the first foundation.
you are in massive existential trouble.
And that immense financial gravity is exactly why these gates cannot just be treated as administrative hurdles. They have to be rigorous.
However, one of the biggest, most pervasive pitfalls highlighted across all our sources is a phenomenon the industry calls gating theater.
Gating theater. I absolutely love that term. What does that actually look like in practice inside a corporation?
Well, we've all probably experienced some version of this in our careers.
Yeah.
Gating theater happens when project teams and executives treat the FEL process as just a massive, bureaucratic paperwork exercise.
A box-ticking exercise.
Exactly. The engineering team works for 6 months. They produce a massive 400-page binder full of checklists, preliminary drawings, and risk registers. They carry it into the boardroom, drop it on the mahogany table with a loud thud.
And the steering committee or corporate leaders just rubber stamped it.
They don't actually scrutinize the data. They don't challenge the assumptions.
They are intimidated by the engineering math, and they just want the future revenue from the finished plant.
So they just check the boxes, eat the catered lunch, and approve it to get to the construction phase. They aren't making real, objective, binary go, kill, or hold decisions.
Which completely defeats the entire purpose of the toll booth. If you just wave every single car through without ever checking their ticket or making sure their brakes work, why have the toll booth at all?
You're just slowing people down for no reason.
Precisely. The psychology and governance behind these gates are vital. These gates are designed to be objective checkpoints for a company board to evaluate risk without emotion.
Because the sunk cost fallacy is a huge enemy here.
It really is. If the project isn't feasible, or if the market conditions have radically changed since FEL1, the absolute best, most profitable thing a steering committee can do is kill the project at Gate 1 or Gate 2.
Have the courage to kill it early.
Exactly. By doing that, they limit the financial damage to just the early conceptual engineering costs. Maybe they lose a few $1,000,000 in engineering hours.
Rather than plunging the company into a multi-billion-dollar construction disaster.
And the sources are incredibly clear on the danger of skipping these steps or faking your way through a gate.
If a project team jumps a gun, forces their way through Gate 3, and enters the execution phase with poor scope definition, it leads directly to the undisputed #1 cause of construction cost overruns globally.
Loss of scope control.
Right. And for the listener, scope creep in construction isn't like adding a new button to a website. What does scope creep actually look like on a massive industrial site?
It looks like financial hemorrhaging, because without a clear frozen baseline defined in FEL3, you cannot tell what was originally planned and what is a new addition.
Give me an example of that.
Okay, if you're building that refinery and the plant manager suddenly decides during construction that he wants a secondary backup power system that wasn't fully engineered in FEL3.
He just walks on site and asks for it.
Right. The construction contractor is going to smile, hand you a change order, and charge you an astronomical premium to halt work, redesign the electrical grid on the fly, and source new materials.
Every single time the scope grows or changes during construction, the schedule slips.
The workforce sits idle, and the budget explodes.
So if the gates are the toll booths keeping everyone honest and preventing that scope creep, how do the project managers and engineers actually do the detailed work inside those phases?
How do they ensure they are driving down costs and hitting their targets?
Right, how do they know their design is actually good? Let's open up the toolbox. We need to look at the specific scientific practices used within the FEL framework to optimize these outcomes.
Because as we've learned, it's not just about an architect drawing pretty blueprints. There's a whole rigorous science to this.
There absolutely is a science to it. And one of the most prominent, widely used tools mentioned in the industry frameworks is the PDRI.
That stands for the Project Definition Rating Index.
This methodology originated with the Construction Industry Institute, or CII. It's a highly structured, comprehensive checklist and scoring method used to objectively assess the completeness of the scope definition at each stage.
And the best way to understand how the PDRI is used is to think of it exactly like a game of golf.
A lower score is better.
Exactly, a lower score is better.
Okay, so how does the scoring actually work in boardroom?
A cross-functional team goes through a massive list of project elements, from the soil testing to the piping diagrams to the environmental permits. They grade the level of definition of each element.
So if a section is completely undefined, it gets a high score, adding points to the total.
If it is fully engineered and locked down, it gets a very low score. A low overall PDRI score, say something under 200 on their specific scale, mathematically proves to the steering committee that the project package is tightly defined.
The risks are known.
And the project is ready to safely pass through the next gate. If the score is high, say 400, it's a giant red flag that the team is trying to push through a half-baked design.
That is a brilliant way to quantify readiness, so executives aren't just guessing based on gut feelings.
It removes the emotion.
And alongside PDRI, I see a lot of references to VIPs, value improving practices.
These are systematic, structured reviews baked right into the timeline of the FEL process.
One of the biggest VIPs is called value engineering. Wait, let me play devil's advocate for a second here.
Sure.
If I'm the owner, doesn't value engineering usually just mean cheapening the product? Isn't that just a fancy corporate term for cutting corners and buying lower quality materials to save a buck?
That is a very common misconception, but true value engineering is entirely different from just cost cutting. It's not about making things cheaper at the expense of quality.
What is it about then?
It is about finding the absolute optimal functional balance. You are balancing the initial capital cost of a piece of equipment against its long-term reliability and its daily operational performance over a 30-year lifespan.
Okay.
If you buy a cheap pump, you save money today. But if it breaks down every month and halts production, your operational costs will ruin you over the next decade.
Value engineering systematically analyzes those trade-offs to ensure you are paying for actual value, not just gold-plating the design.
Exactly. You don't want to overpay for performance you don't need, but you can't underpay and ruin your reliability.
That distinction makes total sense. Now, another critical tool in the VIP toolbox that caught my eye is what's known as a class of facility analysis.
This sounds like a fascinating psychological exercise for the team.
A cross-functional group of executives, engineers, and operators get together in a room, and they are forced to rate their upcoming project on 9 specific competing factors.
Those factors are capacity, product quality, reliability, expandability, lifetime automation, maintainability, turnaround, and schedule.
Yes, and the key word you use there is competing. You cannot have all of them be the top priority.
Right. But if I'm the CEO of a company spending $1 billion on a new plant, why wouldn't I want it to be perfect at everything? Why wouldn't I demand maximum capacity, maximal quality, totally automated, and easily maintainable?
Because if you engineer a facility to be perfect at absolutely everything, you will bankrupt the company before the concrete is even poured.
It's the classic engineering triangle. Good, fast, cheap, pick 2.
It's exactly. The class of facility analysis forces executives to make hard choices about what actually matters for their specific business model. Let's break it down with a comparison.
Say you are building a new pharmaceutical manufacturing plant.
In that industry, regulatory compliance with the FDA and absolute chemical purity are your lifeblood.
So the team will logically rank product quality and reliability as their absolute highest priorities. They will spend immense capital on redundant filtration and clean rooms.
Right, because a bad batch of medicine ruins the company.
Exactly. Conversely, a metric like turnaround, which is the industry term for how fast you can shut down a plant, clean out the pipes, and restart it to manufacture a completely different product, might be ranked very, very low.
Why is that?
Because this specific facility might be dedicated to producing just one single blockbuster drug for the next 10 years. It will never need to switch products.
So by doing this rigorous analysis during FEL, it acts as a guiding compass for the engineering team.
It ensures the design perfectly aligns with management's true business needs, rather than having overeager engineers over-engineer the turnaround capabilities, which would waste millions of dollars on specialized valves and cleaning systems that will never be used.
That is so incredibly smart. It forces the executives to put their money where their strategy is, and it keeps the engineers focused on the main thing.
We also see heavy, sophisticated risk management as a massive tool in the FEL toolbox.
And we aren't talking about a project manager sitting around a whiteboard saying, what if it rains during construction? They're utilizing heavy mathematics.
Yes, the level of mathematical modeling is intense. They use tools like Monte Carlo simulations.
In simple terms, a Monte Carlo simulation takes a project schedule and cost estimate, and instead of using fixed numbers, it uses a range of probabilities for every single task.
It then runs tens of thousands of simulated project executions in a computer, factoring in the probabilities of bad weather, supply chain delays, and labor shortages.
So it basically plays out every possible reality of the project going wrong thousands of times over.
Exactly, and the output isn't a single cost number, it's a probability curve.
It tells the executives, based on these risks, you have a 50% chance of finishing for $1 billion, but if you want 90% certainty that you won't need to ask the board for more money, your budget needs to be $1.2 billion.
That risk quantification is what allows them to set highly accurate, mathematically justified contingency budgets rather than just guessing.
But perhaps the most powerful tool in the entire FEL arsenal when it comes to controlling costs isn't a fancy math simulation at all. It is surprisingly simple in concept, though probably agonizing in practice.
Freezing the design.
Simple to say, incredibly difficult to enforce.
Right. It's just the project manager standing up at the end of FEL3 and saying, pencils down, no more changes. We are building exactly what is on this paper.
Yes, our sources emphatically stress that freezing the design is the absolute most effective way to control scope growth. You lock it in.
Once the design is frozen at Gate 3, any individual who wants to change it, even the CEO, must formally justify the change, explain how they're going to pay for it, and pass incredibly high bureaucratic hurdles to get it implemented.
It essentially makes changing your mind so painful that people stop doing it.
I also really want to highlight another tool from the VIP list, constructability reviews.
Because I think this bridges the gap between the theory of engineering and the gritty reality of construction.
It's not just about an engineer with a PhD sitting in a climate-controlled office in Houston drawing a mathematically perfect, beautiful 3D model.
Constructability is about bringing the crusty veteran construction superintendents into the room during FEL2 and asking the hard, practical, physical questions.
That's right. It's about bridging the gap between the screen and the site. A constructability review looks at a 3D model and asks, okay, this pipe riding is mathematically efficient. But can a massive 200-ton crane actually physically fit into that tight corner of the site to lower this pipe into place?
Or are we designing massive steel structures that require welders to be suspended upside down 100 feet in the air in high winds to bolt them together?
Is there a safer, simpler way to design this joint so they can assemble it on the ground and lift it up?
It's about building a philosophy of physical simplicity and safety into the design before you ever buy a single piece of steel.
And speaking of buying materials, another major cost reduction practice utilized heavily during FEL is multi-project leveraged procurement.
When you realize that 40 to 60% of your total installed cost on these massive industrial projects is just buying raw materials and heavy equipment, finding economies of scale is massive.
If a global chemical company knows they're going to build 3 similar plants over the next 5 years in different countries, they will leverage the FEL phase to standardize the core plant designs.
Then they go to the pump manufacturers and buy the equipment for all three plants at once, negotiating massive bulk discounts.
Which naturally leads right into the concept of modular design. Instead of building the plant stick by stick in the mud, in unpredictable weather with fluctuating local labor rates.
You design the plant to be built in massive modules or chunks in a highly controlled, climate-controlled factory setting, perhaps in a different country altogether.
Then you ship those massive modules to the site on specialized barges and essentially snap them together like giant Lego blocks. But to do that, your FEL engineering has to be flawlessly precise.
But wait, let's step back and look at the sheer scale of this. If you have all these different teams operating simultaneously during the FEL phases, you have financial estimators running massive Monte Carlo simulations, you have civil engineers doing constructability reviews on cranes.
You have procurement teams negotiating global bulk buys for steel, and you have process engineers designing fluid dynamics.
That is a staggering, almost incomprehensible amount of data being generated every single day. How is this actually managed in the modern era? We obviously aren't coordinating multi-billion-dollar projects with fax machines, carbon copy paper, and manila filing cabinets anymore.
We certainly aren't. And that operational reality brings us to the technological shift in project management, the digital backbone.
The modern, successful execution of front-end loading is almost entirely dependent on digital building information modeling, which is called BIM, and the implementation of common data environments, or CDE.
The engineering white papers we reviewed specifically emphasized the critical importance of integrating what used to be traditionally siloed data.
Historically, you had your P&IDs, the piping and instrumentation diagrams, living in one department.
Then you had your E&I diagrams, the electrical and instrumentation schematics living in a completely different department.
And then you had your spatial architectural 3D models living somewhere else entirely. They were separate worlds.
What's fascinating here is the sheer danger of that old siloed approach and why the shift toward data-centric holistic software systems was so necessary.
Let's look at a common historical scenario.
In the past, during FEL3, a mechanical engineer might realize a specific fluid is heavier than expected, so they make a critical update to a piping drawing, increasing the size and power of a main transfer pump.
But because the data is siloed, that update might just live on their desk.
It might not make it over to the electrical engineering team in time.
Oh, I see where this is going.
Right. Suddenly, the electrical team is designing the wiring, the conduits, and the electrical breakers for a much smaller pump. The design gets approved at Gate 3.
Fast forward a year into execution.
The massive upgraded pump arrives on the construction site. The electricians go to hook it up, and the wiring doesn't fit. The breakers instantly trip because the pump draws twice the amperage.
Now, construction halts. You have cascading errors.
You have to rip out the wiring, redesign the power grid, order new breakers, and delay the project by weeks. All because a mechanical engineer didn't walk across the hall to tell the electrical engineer about a change.
It's like my absolute favorite analogy for siloed work. Imagine trying to write a complex, 1,000-page, intricately plotted fantasy novel where 3 different authors are locked in different rooms.
Writing different chapters in different languages.
And they are completely forbidden from ever sharing their notes or character arcs. The final book would be an unreadable disaster.
That was old engineering.
But now, utilizing modern, sophisticated digital platforms like AV-EVA Unified Engineering, it's like all those authors are essentially typing in the exact same shared Google Doc in real time.
That's a perfect analogy. A unified data-centric approach ensures that a single, incorruptible source of truth is maintained throughout FEL1, FEL2, and FEL3.
These systems utilize default class and attribute models to maintain strict data quality and interoperability.
They track the millions of components in the bill of materials instantly.
So now, if that piping engineer changes the pump to a larger model in the software, the electrical engineer's digital dashboard lights up immediately,
automatically highlighting the new power requirements and flagging a clash.
This digital integration significantly, profoundly lowers the risk of interface clashes when you finally move to the physical construction site.
I love the theory. I love the frameworks. But I really want to see all this high-level theory, these rigid stage gates, and this massive digital coordination actually put into action.
I want to say how it saves the day. So let's pivot and look deeply at a real-world case study provided in our sources, the $600 million EV battery plant.
This case study is a textbook, perfect illustration of the FEL process working exactly as designed under extreme corporate pressure.
The context here is a specialty chemicals company. They have determined they need to build a massive $600 million greenfield plant, meaning starting from scratch on an empty piece of land to produce critical materials for the surging electric vehicle battery market.
The CEO has issued a very strict mandate to the project team. They absolutely need speed to market. The EV boom is happening right now, and if they don't have a plant running soon, they lose market share.
But simultaneously, the CEO is terrified of cost overruns because a previous project nearly bankrupted a division of the company.
Talk about a high-stress environment. So how do they actually apply the FEL framework to solve this? They don't just start digging, they start with FEL1, the opportunity framing.
The project team sits down and formally frames three distinct options to meet the CEO's goal. Option 1. They could debottleneck and aggressively expand an existing, older chemical site they already own in the Midwest.
Option 2, they could build a brand new, highly modular plant near a major coastal port.
Option 3. They could avoid construction altogether and partner with a third-party toll manufacturer who already has a plant, paying them to make the chemical.
And in FEL1, they don't guess. They run the rough order of magnitude estimates, the logistical modeling, and the market analyses for all three options.
The toll manufacturer option seems fast, but the profit margins are terrible.
Expanding the old plant seems cheap, but the logistical nightmare of shipping the finished product across the country to the ports kills the economics.
The winner. The modular greenfield plant near the port. It offers the best net present value, or NPV.
Let's define that really quickly for the listener. NPV, net present value, is basically a financial metric that calculates the current total value of a future stream of cash flows minus the initial investment, taking into account the time value of money.
It tells the CEO, in today's dollars, which of these three options will ultimately make the company the most actual cash over the next 20 years.
Exactly. And the coastal plant won the NPV calculation with an acceptable risk profile.
So, having made that data-backed go decision at Gate 1, the steering committee approves the funding to move the team into FEL2, the selection phase.
Here, they get more granular. They screen 2 different core chemical processing technologies with specific vendors.
They shortlist a highly specific coastal site that already has existing rail access.
Because they do those early constructability and logistics reviews we talked about, the engineers realize they can significantly compress the construction schedule by modularizing the process skids.
Meaning they will build the highly complex chemical processing units off-site in a clean, controlled factory in another state and literally bring them into the coastal site on heavy trucks, fully assembled.
Exactly. They also narrow down their contracting strategy during FEL2. They decide they will use a primary EPC contractor for the main chemical blocks, but they'll carve out separate specialized contracts for the massive tank farm and the rail spur integration.
They present this refined concept at Gate 2, and the board gives them the green light to proceed to the heavy lifting.
So they pass Gate 2 and enter FEL3, project definition. This is where the FEED is completed. They completely freeze the basis of design. No more changes.
They run their massive Monte Carlo probabilistic schedule, and they set what's called a P50 of 28 months.
That simply means that, based on all the simulated risks, they are 50% mathematically confident they can hit a 28-month construction schedule.
But here is the critical project saving moment. During their deep dive risk analysis in FEL3, the data flags a major looming supply chain bottleneck in the global market for specialty alloy vessels.
These vessels are highly specific, custom-forged pieces of equipment with incredibly long lead times. If you order one today, you might not get it for a year and a half.
If we connect this to the bigger picture, this exact moment is where front-end loading proves its worth 10 times over.
Because the team systematically identified that specific alloy bottleneck during FEL3 before the final investment decision, the management team makes a highly strategic, calculated decision.
They decide to pre-procure those long lead reactors. They write the purchase orders and buy them early while still in FEL3, essentially protecting their critical path from supply chain shocks.
When they finally present this meticulously defined, risk-adjusted package at Gate 3, the board is confident, they approve the FID, and the $600 million is unlocked.
So what does this all mean for the actual outcome of the project? Did it work?
The sources show that because of the specific decisions made during FEL, the modularization strategy pulled their mechanical completion date in by a full 12 weeks compared to what a traditional stick-built plant would have taken.
That's 3 extra months of selling easy batteries.
And because they had the foresight to pre-order those reactors, when the global supply chain volatility actually hit the market a year later, it didn't touch them. Their vessels were already being forged.
The project ultimately finished within its risk-adjusted contingency budget and hit the market window perfectly.
It is the ultimate example of risk mitigation quantified. Think about the alternative. Without the rigid discipline of FEL, that CEO's intense demand for speed would have almost certainly resulted in the team skipping the options study, rushing straight into construction on the very first idea they had, and pouring the concrete.
They would have erected the steel structures, and then they would have hit a brick wall.
They would have had hundreds of highly paid union workers standing around an empty lot for 8 months doing nothing, waiting for those specialty alloy vessels to arrive, simply because no one took the time to foresee the supply chain bottleneck.
By spending extra time and a little extra money in FEL 2 and 3 to thoroughly map the risks, they saved the entire project timeline and protected the company's bottom line.
It is an incredible success story, and it really validates everything we've been talking about.
But, as with all business frameworks, it is not a magic wand. It's not a silver bullet that works perfectly in every single scenario. Which brings us to the crucial nuance of our final section, the flip side.
We need to look critically at the limitations, the differing perspectives in the industry, and the common pitfalls that can derail this entire process.
Because it begs an obvious question. If FEL is so undeniably great at saving money, why isn't it used rigorously on every single commercial construction project everywhere in the world?
That is a very perceptive question, and our sources point out a fascinating dynamic in the industry. FEL is notably less common and often less rigorous in projects that are directly organized and led by EPC contractors or equipment suppliers, as opposed to projects led by the ultimate owner-operators like the chemical companies or oil majors.
And the reason for this comes down entirely to differing financial incentives.
Contractors, by their very nature, are primarily focused on execution efficiency and volume. They want to win the bid, get onto the site, build the facility exactly to the provided specifications, and get out to move on to the next job.
They generally aren't as interested, nor are they incentivized, to participate in the broad, philosophical, conceptual exploration of an FEL1 options study.
Right, because their financial risk exposure is much lower during that early phase. They often legally pass the conceptual risk back to the owner. If the owner picks the wrong technology, the contractor still gets paid to build it.
Plus, a pure construction contractor might not even have the highly specialized early design process engineering capabilities on staff required to run a proper FEL1 study. They employ construction managers, not necessarily metallurgical research scientists.
Exactly. This creates a very real, very palpable tension between owners and contractors. The owner wants a rigorous FEL process because they are trying to protect a billion-dollar investment across its entire 40-year operational life cycle.
The contractor just wants to be told exactly what to build, as quickly as possible, so they can execute efficiently and maximize their profit margin.
Because of this tension, we see two distinctly different management approaches to how FEL is funded and categorized. Some progressive organizations treat the FEL phases as a non-project activity.
They fund it out of an R&D budget or a corporate strategy budget. This allows the engineering team highly flexible exploration and innovation without the strict, punitive constraints of an official project budget and a ticking clock.
Others, however, treat it strictly as the initial phase of the official capital project itself, which means the clock is ticking from day one, which can add unnecessary pressure to the conceptual thinking.
There are other major structural limitations to consider too. FEL requires a massive front-loaded effort. You are walking into a boardroom and asking executive management to authorize spending $20, $30, or $40 million on engineering hours, software licenses, and consultants before they ever see a single stick in the ground.
For a lot of impatient executives who are driven by quarterly earnings reports, authorizing that kind of spend for paperwork is a very hard pill to swallow.
And as we discussed with the gating theater problem, if you aren't vigilant, the process can easily devolve, becoming overly bureaucratic, adding layers of approvals and delays without actually improving the quality of the engineering thinking.
Another severe, highly relevant limitation in today's world is the danger of what the industry calls static bias.
The reality is that executing FEL 1, 2, and 3 thoroughly takes months, and on mega projects it can take years to complete.
If massive, unpredictable market shocks happen during that extended time, like sudden hyperinflation A global pandemic, a war that spikes energy prices, or unprecedented supply chain chaos, and the project team fails to dynamically refresh the underlying assumptions of their FEL data, their pristine estimates will be completely catastrophically wrong.
That makes total sense. You cannot treat an FEL2 cost estimate that was carefully calculated in 2019 as the gospel truth for a project that is finally breaking ground in 2022. The price of steel might have tripled. The cost of labor might have skyrocketed.
If you don't refresh the data before Gate 3, the project will instantly blow its budget the minute it enters execution.
Precisely. You also run the immense risk of locking in too early, which is the flip side of rushing. If a project team feels intense corporate pressure to pass a gate and show progress, they might prematurely freeze a suboptimal, clunky engineering concept just to keep the momentum going.
And because of the permanent, concrete nature of capital projects, freezing a bad design at Gate 2 isn't like shipping a buggy piece of software. It can institutionalize a terrible, inefficient operational flow that the plant workers will have to suffer through for the next 40 years of that facility's life.
And finally, a very common and often disastrous pitfall highlighted repeatedly in the texts is the issue of misaligned estimate classes and contract types. This is where the business side clashes violently with the engineering side.
Imagine a project team gets to Gate 2. They only have a loose Class 4 scope definition, meaning they know generally what they want, but the cost could still realistically vary by 30 or 40%.
But the executive management team demands absolute price certainty for their quarterly report, so they force the project manager to go out and award a lump sum, fixed-price contract to an EPC construction firm based solely on that loose Class 4 design.
Oh boy, that is a guaranteed textbook recipe for disaster.
It seems like it. Why would a contractor even agree to that?
Sometimes they agree because they need the backlog of work or they plan to aggressively use the change order process to make their profit. But forcing a fixed price on a loose design is a recipe for massive change orders, ferocious legal lawsuits, and bitter project stalling disputes.
You simply cannot ask a contractor to absorb the massive financial risk of a lump sum contract when you, as the owner, haven't done the rigorous FEL3 work to define exactly down to the inch what they are supposed to be building.
The contract type, whether it's lump sum, cost reimbursable, or time and materials, must absolutely align with the maturity and definition of the design.
Which, bringing it all full circle, perfectly underscores why this entire front-end loading framework exists in the first place. It protects everyone involved.
It really does.
Well, we have covered a truly massive amount of ground today. From the foundational anatomy of the cost influence curve and the realization that fixing mistakes early is the key to survival, to the disciplined, rigorous, stage-by-stage march through FEL 1, 2, and 3.
We've explored the critical, unyielding go-kill toll booths that protect a project's financial viability, the unified digital systems that keep the engineering data pristine, and the very real human and market pitfalls that can derail the whole thing.
The overarching, undeniable key takeaway for you listening right now is that whether you are tasked with building a billion-dollar oil refinery, launching a massive new enterprise software platform, or reorganizing a global supply chain, front-loading your critical thinking and rigorously, painfully defining your scope early is the ultimate way to de-risk any massive investment.
Yeah.
You absolutely have to take the time to do the right project the right way before you ever try to do it fast.
It is a profound lesson. We spent this entire deep dive looking at how massive multinational corporations use the discipline of front-end loading to build billion-dollar infrastructure and manage immense financial risk. But I want to challenge you to think about this on a much more intimate scale. Think about your own life. Think about your major career pivots, your decision to go back to school, your major financial investments, or moving your family across the country, your personal mega projects. How often do we rush straight into the execution phase of our own lives because we are desperate to see immediate progress, or because we feel societal pressure, completely skipping our own FEL1 options study and our own FEL2 concept selection? We just start building.
We do.
What if the secret to avoiding our own personal cost overruns, our own burnout, and our own schedule delays isn't just grinding harder in the execution phase, but finally having the courage to pause, step back, and take the time to truly front-load our own life's design?
Wow. I absolutely love that perspective. Front-loading your life's design. It's about doing the hard thinking before you start laying the bricks. Thank you so much for joining us on this extensive, deep dive exploration of project management mastery and the realities of capital construction. We hope you walk away with not just a new perspective on how the biggest physical things in the world are actually built, but perhaps a new mental model for tackling the biggest projects in your own life. Until next time, keep questioning, keep learning, and keep digging deep.